Good afternoon, everybody. It's a great honor to introduce the President's invited speaker for JSM 2011, Sir David Cox. Sir David's education began at St. John's College, Cambridge, where he studied mathematics. During the war, he worked for the Royal Aircraft Establishment and then received his PhD from the University of Leeds. While working on his PhD, he also was a researcher at the Wool Industries Research Organization. From 1950 to 56, he worked at the Statistical Laboratory in Cambridge. During this period, he also served as a visiting professor at Princeton, Berkeley, and UNC Chapel Hill. For the next 10 years, he was a reader and then professor of statistics at Birkbeck College, London. He then spent 22 years as a professor of statistics at Imperial College, London, including 4 years as head of Department of Mathematics. For 5 years, while at Imperial College, he served as a senior research fellow for the Science and Engineering Research Council of the UK. In 1988, he became warden of Nuffield College, Oxford, a position he held for 6 years. Since 1994, he's been an honorary fellow of Nuffield College. Dr. Cox's contribution to theory and applications of statistics are influential and pervasive. His seminal work on proportional hazards models transformed medicine as well as other areas. He is the author or co-author of over 300 articles and 20 books, and has richly influenced the professional and personal lives of thousands of students and colleagues. Indeed, it might be interesting to develop a Cox number similar to the Erdos number in mathematics. His awards are numerous. He has received 20 honorary doctorates. He's received the Guy Medal in Silver and the Guy Medal in Gold from the Royal Statistics Society. He is the first non-medical researcher to win the Kettering Prize and Gold Medal for cancer research. He's received the Weldon Memorial Prize from the University of Oxford, the Max Planck Research Award, and the Copley Medal just last year from the Royal Society. He's the second statistician to win the Copley Medal, the other being R.A. Fisher. He was knighted by Queen Elizabeth II in 1985. I was delighted when Sir David accepted my invitation to speak at this JSM. I know you'll be delighted by his address entitled Statistical Analysis, Current Position, and Future Prospects. With great pleasure, I introduce you to our distinguished colleague, Sir David Cox.
Well, good afternoon, everyone. There has been a sort of rehearsal to check that I am audible in the remote fastnesses of this room over there and over there. Can I be heard? If not, please convey this in the usual way. Madam President, I very greatly appreciate your invitation. Thank you very much indeed. The program for this meeting, like all big statistical meetings, is deeply impressive, not so much because of the wide range of statistical ideas that are involved, as the wide range of applications. We find statistical ideas involved in very many areas of the physical, biological, and social sciences, in aspects of public policy, in business, and in everyday life. Sometimes the statistical involvement is relatively small, sometimes it's quite appreciable, sometimes it's absolutely crucial. And this makes our subject a particularly exciting one, but it also poses some challenges. First of all these applications, if looked at in depth, are a bit different, sometimes very different. And yet we need to preserve some unity to the subject. Specialization and fragmentation take place and are to some extent unavoidable, but somehow or other we have to bring together the notion that some parts of our work are highly specialized. At the same time, we have general ideas that contribute very widely. And most of my talk today is going to be implicitly about that theme of the specialized nature of particular applications, and yet at the same time the wish to see some generality. And it may help to begin by my checking that I can use these complicated pieces of equipment, possibly, with the following idealized model of a research issue. Question or questions arise. Are there data that might answer those questions? If not, design a study that will or partly will. What are we going to measure? What do our measurements actually mean? What's their purpose and what's their reliability and so forth? Various phases of the analysis of data, some largely descriptive, data auditing, so on and so forth, and the more formal methods of statistical analysis that we spend in the more academic side of the subject a great part of our lives studying. And then finally, I put this last phase, interpretation, by which I mean translating the results of our statistical analysis into scientific interpretation of the subject matter or the implications for public policy or whatever the issue might be. Now that's a model, if you like. It's an idealized progression in various senses of the term. First of all, a particular individual may well enter this process at, I see. You don't want to see me, for goodness sake. That's a very bad idea. Especially when I'm talking about measurement. And the reliability of data. Well, yeah, that's quite off-putting. Now, what was I going to say? Well, first of all, it's idealized in the sense that a particular individual, particular statistician, may well enter this process, perhaps at the analysis stage. But that doesn't mean the design can be ignored. I mean, only a week or so ago, a friend of mine told me that she'd been asked to take over the analysis of a big nutritional study. And on looking into it very carefully, she found that the control group in the study, while it seemed to have been selected by a legitimate procedure, in fact it managed to exclude all vegetarians. And if she hadn't detected that, of course, very misleading results could have been obtained. And then the issue is, of course, then, having discovered it, what can be done to resurrect the security of the investigation. But there's a deeper sense in which it's an idealized progression that may well be quite a good model for areas where there's a very set and well-established process of investigation. But in newer areas, or where a big study is being set up in a field for the first time, and particularly if the investigation lasts for a year, 5 years, 10 years, or so on, it's very likely that during the course of that one would be led to change the formulation of the questions. This may, in some contexts, be the most important thing to learn. That aspect depends very much on the natural time scale. It's sometimes useful in a field to say, what's the natural time scale of an investigation? Between thinking of a problem, is it a week before you can get an answer, a month, a year, 5 years, 15 years? And the length of that time period has an impact on the general strategy of analysis. I'm not going to say very much about design. Beyond this, There are, of course, the traditional divisions between experiments and observational studies, the various kinds of observational study, cross-sectional, longitudinal, prospective, retrospective, and so forth. But I think, particularly in teaching, and by teaching I include when we're teaching ourselves, sometimes, I mean, the most important part of teaching is when we're teaching ourselves, in the sense when we're the only student who's listening. We may listen better than some of our other students, of course. The need to see this in a or to recognize these distinctions and their aspect for interpretation, but at the same time to see that there can be all sorts of interesting possibilities of mixed investigations, but also that in a certain sense the goals are common: to avoid systematic error, to try and control random error, to get an estimate of the amount of random error, and particularly to get answers to focused questions. And so I think we need a more unified view of design. Measurement is such an enormous topic, I'm not going to say a great deal about it. Are our measurements relevant? What about their dimensionality? If you're interested in the health, quality of health-related life, quality of life, how many dimensions do you need in a particular context to do that? The reliability of methods of measurement and the avoidance of a Heisenberg effect. Analysis comes under a number of phases, ending up with the formal analysis. And I'm going to spend almost all the rest of the lecture about formal analysis. That's to say, analysis based either occasionally on a purely algorithmic approach, but more likely on a probabilistic model. And of course, the literature, the more theoretical literature of our subject, concentrates overwhelmingly on that aspect, but I suspect that the day-to-day life of those of us who work as applied statisticians, which I do to some extent, is concerned with a lot of other things as well. So I'm going to look at a number of examples. And the first of these... No. Okay, there's another slide needed. That's what I want. Now, this is an organism called Sordaria, and Sordaria is a fungus which botanists study in the laboratory. It's quite small, and the essence of it, that in the fungus there are sets of 8 spores. And this is a diagrammatic representation of Sordaria, not a photograph. There are sets of 8 spores. They're ejected from time to time, and when that happens, any link in this chain may break. So a whole set of 8 may be deposited spores as a single entity, or at the other extreme, every link in the chain may break, and you get 8 single spores, and then every partition of the integer 8 is possible. Now, what botanists do is put this organism in the laboratory, let it eject its spores under standard conditions of, for example, temperature, if that's what they're interested in studying, and at the end count up the numbers of spores of various types. If you look at the upper diagram there, the left-hand point is the number of single spores, the next point is the number of pairs, and the right-hand end is the number of whole sets of 8 that have been ejected intact. And the interest is to study how those distributions change. Now, the first step is we can think of a probability model for that, in which, in effect, we imagine this process going on and on and on forever. Of course, a fictional idea, but nevertheless can be achievable to a close approximation. Those are frequencies based on 1,000 or so spores. And you see they're getting pretty smooth, and the notion is if we had more and more that we get a smooth curve. And the underlying probabilities represent that. They represent, in somewhat idealized form, the biology of the system. They're not about knowledge. They'd be there if we hadn't any data. And a lot of the statistical models we use are like that. They're purely empirical. in the sense they describe patterns of variation as we see them in the real world, and logistic regression, least squares regression, the weird methods people sometimes use to analyze survival data, and all these have no science in them in the sense that they're just empirical representations of behavior, and from that they get their very generality and importance, but also they lack their focus on the scientific objective. Now, in this particular example, we can go a stage further because we can very easily construct a little theory of what's going on here. Remember, the basic idea is we have these chains of 8. Let me try and go back. We have these chains of 8, and as each is ejected, we might think of a little model that said there's a probability theta that every link in that chain breaks independently from link to link and independently between different sets. That would be a little probability model that described what was going on. And then we could work out something about what we observe. I mean, first of all, of course, the probability that we observe a whole set of 8 is 1 minus theta to the 7th. The probability that we observe 8 single ones is theta to the 7th, and so on. But it is a bit more complicated than that, because the unit of study, the unit of investigation is one of these sets of 8. But remember that each of those may generate one data point, namely a set of 8, or it might generate 8 data points, 8 single spores, or anything in between. So there's a rather complicated relation between the underlying process and what we're actually observed, because the botanist just goes to the lab at the end of some days and just counts up how many, what's there. So we have to do a little bit of mathematics to get that, and we get those not very interesting formulae. The probabilities are rational functions of theta. And now we have two problems. Now, in a sense, we're now at a point where tens of thousands of pages of statistical theories start. We've got a parametric model for our data, and we ask two questions. Can we fit the model, in other words, estimate the parameter theta, and is the model any good? I mean, the model may be absolute, for all we know for those formulae, the model may be absolutely hopeless at describing the data. There are always these two aspects. And all the main approaches to statistical inference start by saying we will write down the likelihood function, which is the probability of what we've observed given the value of theta. And the difficulty here is you can't do that because you haven't observed enough. For example, every time you observed a 7, there must have been a 1 that went with it. Every time you observe a 6, there were either a 2 or 2 1s, and you don't know which. So the frequencies are intertied with one another because of the method of collecting the data. So we can't calculate the likelihood function, and as such, this is, in a way, representative in very simple form of a class of problems in systems biology and phylogenetics that are being actively considered at the moment, where likelihoods, although in principle might be available, can't be calculated for some reason. But this is a very particular example because some thought will show a very in some ways a rather curious fact that although we can't find the likelihood, we can find the sufficient statistic that we would calculate if we were able to get the likelihood. Therefore, we can estimate the parameter theta, and therefore we can calculate the fitted values, and we can look at them, which is the most powerful way of testing goodness of fit. And there you have the smooth, sorry, I'm confusing myself. There you have the smooth fit to the data, and the smooth fit is the corresponding values from those formulae that I showed you. And the botanists looked at that and said, great, the fit is totally adequate for our purpose. The data, the thing that's being explained. And what that leads on to is estimating theta and studying, for example, how it depends upon temperature, because the viscosity involved in the organism is temperature dependent and the viscosity affects what happens when the spores are ejected and so on. So the fit was adequate. Because it does raise the question, had it not been, how would we have tested goodness of fit? And I'd just point out here that the principle of sufficiency in statistics answers that. So the principle of sufficiency says the data can be divided into two parts. The sufficient statistic, which, given always the model, the sufficient statistic tells us about the unknown parameters. But the conditional distribution, given the sufficient statistic, is a fixed distribution in principle known. And by looking to see whether the data are more or less conformable with that known distribution, we test the adequacy of the model. And I think I'm right, but I'm open to contradiction, that all known tests of model adequacy really depend on that principle, or they're not normally formulated in that way. Of course, by sufficiency, we mean sufficiency in the strong sense in the exponential family of distributions. Otherwise, we appeal to M.S. Bartlett's a notion very strongly developed from the beginning at great depth by Le Cam, that maximum likelihood estimates are approximately sufficient. So how one would proceed to test adequacy here is two things. First of all, we've got to decide what feature we haven't an alternative model. This is a case of testing significance where there's no explicit alternative. The alternative might be, though, that each set of spores has got its own theta, and theta's got a distribution across the set of spores, a kind of hierarchical model for theta. And some thought would show that what that would do would produce more ones and more eights compared with constant theta. And it's interesting that all three graphs have a slight excess in those two positions. There is an alternative explanation that some sort of contagion is going on, that each set of spores is a kind of finite Markov chain. That's probably less plausible. Well, to test the significance of that, what one would do in principle would be to simulate a large number of realizations, preferably with exactly the same maximum likelihood estimate as the data. If not, a large number of realizations, pick out those that have got maximum likelihood estimates close to what's observed, and then look within that set of ensembles as to whether the things we've got there are typical or not. So that's how goodness of fit, how the two phases would go, following from the sufficiency principle in both cases. So we've got fit a model, check its adequacy. And I want to contrast what we do, what's conventionally done in statistics, with what's normal in classical physics. By classical physics, I mean physics ignoring quantum and relativistic effects. There are the classical laws of that subject, which one could think of as like models. Let's pretend they're models. Newton's laws of motion, the Navier-Stokes equations, Maxwell's equations of electrodynamics. Now, suppose a physicist collects some data on a moving body. He or she measures the mass of the body, measures its acceleration, measures its force, looks to see whether Newton's law is satisfied, and finds that force is not equal to mass times acceleration. The model doesn't work. What does the physicist say? He doesn't say Newton's laws are wrong. He says, my data are defective. He says, I have forgotten or omitted to measure a component of force that is acting on this body. And you can say very precisely what the vector magnitude of that force is. It's exactly what's necessary to make Newton's law hold. So you then study this under various conditions and you isolate what the force is and so on. And that has proved, I think, a sort of argument, a very, very, very powerful argument in physics. Of course, it's totally counter to what we normally do in statistics, which is to say, well, we don't really believe our models very much anyway, and so if they're defective, if there's a clear lack of fit, we better do something about it, and there are various things we can do, ranging from ignore it and press on, to developing a wholly new model. Are there any instances where one might do something more like the classical physicist. Well, I think there might be. This is very speculative. This, excuse my terrible shaky handwriting, this is a very, very idealized representation of the sort of thing you see a lot of in epidemiology in particular nowadays. 3 time periods, t equals 0, t equals 1, t equals 2. At t equals 0, there's an exposure or treatment which one takes on various forms. At t equals 1, there's some measure of, hopefully, its effect. I've put blood pressure after 2 weeks of treatment, let's say, and at t equals 2, we get some outcome measure. And then we follow the area of graphical Markov models or of really developments of Sewell-Wright's path analysis. We look to see what the dependencies are. We may find that the output measure, the cardiovascular event, depends on blood pressure and on the treatment, and there's a direct path. We split the dependence of the response measure on the treatment into 2 parts, that's conditioned by the intermediate measure and that isn't. And the direct the arrow at the top is sometimes, I think quite misleadingly, called the direct effect. Now suppose we were to say, and this would only be relevant in certain very special contexts, supposing we were to say, we think we're observing a Markov process. Now in a Markov process, if you know the state at time t equals 1, the past and the future are independent. What that diagram says, it's not a Markov process, because if it's a Markov process, that direct path from the treatment to the cardiovascular event or whatever it is shouldn't be there. Now, if we thought it really... Now, in a certain sense, everything's a Markov process, because if you have a sufficiently rich state space, almost everything, well, perhaps everything in terms of stochastic models becomes a Markov process. But supposing one looked in a more practical sense, hoped it would be close to a Markov process in some reasonable sense. Then what that picture would say, we've forgotten to measure something at t equals 1 that would explain that so-called direct path. Let's look and see what it is. And that would be exactly analogous to the physicist saying Newton's laws aren't satisfied, we must look to see why they aren't satisfied. So I think, while I've never seen that argument actually used, probably it has been somewhere or other, it seems to me a potentially useful one. Well, I've summarized it there. There are 3 roles of a stochastic model. The middle one is just a description of patterns of variation. The top one is a theory, a scientific theory, of which I've given you a very primitive example of the data generating process. And the third aspect, which also comes into this problem, is that if the data capture process is relatively complicated, we may need a stochastic process to develop it. If we would like to have done simple sampling, and we've actually done length bias sampling, we need a bit of statistical theory to link between the two. Now, some developments from that. I already mentioned the fact that in systems biology and elsewhere, there's interest in very complicated models, parametric models, for which the likelihood function can't be calculated in any useful sense. And there's the ABC algorithm has been developed with that in mind. If you Google ABC, you'll find it says artificial bee colony algorithm. And that's a rather strange algorithm in optimization theory, which models a system as a model of swarming bees. Well, that isn't what this ABC is. ABC stands for A for approximate and C for computation, and B, not surprisingly, for Bayesian. So approximate Bayesian computation. Whether it has essentially to be Bayesian is a minor issue. But that's a procedure that's being actively studied for dealing with these complicated models. As I said, we can evade it in this problem here because of this sort of accident that the sufficient statistic can be calculated. There are an enormous number of other developments. I've given you a very, very simple stochastic model. Of course, there's a great, and in my mind, fascinating literature connected with stochastic processes and their role in trying to explain data, in particular via the role of so-called toy models, that's to say models that try and capture the essence of a complex phenomenon like, say, an epidemic in relatively simple differential equations, deterministic or probabilistic. Now I want to turn to a different subject, what I think the physicists have somewhat strangely, to my mind, named discovery. And this is essentially looking for a needle in a haystack. I assume, there's a great danger for British people to use bits of expression that are not familiar. Is the expression needle in a haystack? It's okay. Good. One has to check these things, you see. So we're looking for a needle in a haystack, and there's a lot of noise around. And I think it's important, I'm going to give some applications in a moment, that to distinguish at least two, perhaps more than two, main situations. First of all, perhaps there isn't a needle there at all. Perhaps the Higgs boson doesn't exist, which is the thing. Or you select quite a few, you see quite a few needles after you've searched for a while. You want to, following Benjamini and Hochberg's important paper, you want to control the so-called forced discovery rate. In other words, you want to ensure that most of the needles you claim to have found really are needles. Those are two slightly different problems. Applications, particle physics, already touched on, genetics. The GWAS looking at vast numbers of possibilities for detecting, say, an association between a disease and a genetic phenomenon. A perhaps less obvious application is the following. Think of a big multiple, let's say, logistic regression in sociology. One studying the effect of some relatively simple response variable on a large number of potential explanatory features by the kind of empirical regression that is fairly commonly used in that field. The practicalities are that one fits linear logistic regressions, that the dependence on the explanatory variables is linear, and yet, of course, it's highly implausible that complex social phenomena are really linear. So what one can do about it is to say, well, perhaps in there are a few nonlinearities and a few interactions, and try and look for them. So in a complex case, the needles we're looking for are the nonlinearities or the interactions in this complex system. In a situation where if you put into your model all possible nonlinearities and all possible interactions, you'll be in a hopeless situation. So that's a broad analogy. And as I said at the beginning, all problems are different. I am not saying these three things are the same. I'm saying there are relations between them. Now, there are a number of different approaches. I'm going to concentrate on the case where our data consist of a large number of p-values, the results of significance tests. Of course, it's open to question whether that is the right place to start, but let's assume that it is, and that they're treated as independent. Now, the study of what to do with a large number of p-values was first investigated by two Norwegian statisticians, Tore Schweder and Emil Spørsvold, 25 years ago, and they concentrated on the p-values. But it's much better, just from a presentational point of view, to take instead of p, take minus log p. And that's because we're interested in this case in the very small values of p. So rather than looking at how the very small values of p concentrate near the origin, one's looking how the large values of z, I have to remember to say z, the large values of z stand out on their own when we look at them. And what we can do is to note that if the different p-values are independent and uniform distributed, which would correspond to a global null hypothesis, then the z-values are independently exponentially distributed with mean 1. And there's a beautiful result in probability theory called the Rényi decomposition, after Alfred Rényi, the Hungarian probabilist, which tells us the statistical structure of these ordered values, essentially that they form a Markov process of a particular kind. And so we can use, if we go to more sophisticated methods than just plotting the results, we can appeal to properties of this Rényi decomposition. Now, I gave a talk about this at CERN, the European Nuclear Physics Facility, a few months ago, and the paper, a short paper, was sent to Brad Efron at Stanford for his comments. And Brad, who's published about almost exactly a year ago, a very important monograph on, IMS monograph on the subject, basically the subject, he applied what I'd suggested to one of his sets of data, 6,000 genes, for a possible connection to prostate cancer. And here's the plot that Brad provided. Now, the vertical axis is minus log p. The horizontal axis is, and these 6,000 values of minus log p are put in order, small ones near the origin, large ones at the right-hand end, and plotted against their expected values if the overall null hypothesis were true. And the bottom scale is more or less a logarithmic scale. Other people have made plots. David Clayton in Cambridge has made similar plots with genetic data. Now, what are we to make of that? If the overall null hypothesis were true, the point source should lie on the dotted red line. Now, very obviously they don't. You don't need, almost any method is going to show that. What Brad did was to say that the blip, now this is where I need to try and use this pointer, but there's a blip which somewhere there in the plot, which indicated that approximately 30 of the genes had an association with prostate cancer. Now, another interpretation is the following. You can show that, well, what we're doing is doing a large number of significance tests and going down and down and down to very small values of p, very, very high levels of significance. And Brad himself has made this point, that however good our statistical theory, is it really plausible that it's going to hold up in these extreme areas? I understand in the GWAS there's a sort of convention that something like a p of 10 to the minus 8 is needed. In the particle physics area there's more or less a convention that about 10 to the minus 7 is needed. But do probability calculations really mean anything down this area? And you can show that if our statistical theory of our tests was pretty good, but went wrong in the tails, that the distribution in the tails was different from the null hypothesis, that should be a smooth curve. And so a different interpretation of that plot is that that's a smooth curve, and all that it's telling us is that there's no particular individual genes that are standing out, that it may all be an artifact of a statistical failure in the tails of our distribution. Now, of course, the ultimate test is whether any of these findings have been replicated, and I don't know, and I think Brad doesn't know the answer to that question. So that's... now I want to turn to the third example, and this is bovine tuberculosis. Now, bovine tuberculosis is of great concern in some European and other countries, in New Zealand as well as the European countries. I think it's of no concern in the US, except in a smallish area of Michigan, where it is, I understand, an issue. And bovine TB is a disease that occurs very often in cattle, by its name, and wildlife. In Michigan, in deer, in Britain, in the European badger, in New Zealand, in the possum that was introduced from Australia at some point. And, well, I had to have a picture, and my friend Crystal Donnelly provided this photograph by Richard Yarnell, which shows two badgers grooming one, or one badger grooming another badger. And badgers are very kind of emotive animals. They figure prominently in English children's stories, always benignly. But in fact, they're quite large. They're nocturnal, and they do certainly carry the disease of tuberculosis. I'll go this way. Well, let me just say a few more words. The disease is caused by an organism, Mycobacterium bovis, which is not the same as the primary cause of tuberculosis in humans, which is M. tuberculosis, or in birds, which is M. avis, although they're very similar. And before the pasteurization of milk, M. bovis was a very common cause of TB, especially in children, but no longer so in developed countries. But in Britain, there's strong evidence that both badgers and cattle carry this disease. There are strong economic consequences for the health of the cows, but also some human risk, because if the disease became very widespread, there'd undoubtedly be a public health concern. Now, a group of us was set up some 12, 13 years ago to plan a program of research on bovine TB, and only one component of that was a randomized trial. And I want to talk just a few minutes about this randomized trial. And it had the form of essentially a randomized block design, that it consists of sets of 3 areas, and each colored area is going to be an experimental unit. They were originally circles, but they had to be, the boundaries had to conform with farm boundaries, and of course they didn't want to go into the sea, obviously, nor did they want to go into urbanized land. So that's their strange shape. They're placed in regions of high historic incidence, and there are 3 of them in sets of 3, and they were randomized between 3 different things. All the regions were surveyed, and then one region was randomized to no treatment, to remain a survey-only region. One was subject to proactive culling. That's to say, every year a team of 50 field workers would come to the region and do their best to shoot as many of the badgers as they possibly could, and then they'd go away and the next year come back again. And that was called proactive culling. And reactive culling was waiting for a TB case to occur and then to cull in the region surrounding it. So there were those 3 treatments. As each area became available for study, it was randomized. So there were 10 separate acts of randomization. And the randomization was thought to be very important because this is a highly contentious issue, for a reason I'll explain later, in the UK at least, I think in other countries. And if we hadn't randomized, not only might there have been a possibility of bias, but there most certainly would have been accusations of bias. So the randomization was publicly witnessed. And the Ministry of Agriculture headquarters in London are close to Westminster Abbey. And I recall at one occasion a clergyman was brought around to witness the randomization of a particular triplet. It was explained to him exactly what we were doing and why, but I think he went away mystified by the arcane ritual that he'd observed. But the randomization here was, I think, quite important, both to give us some reassurance about equity, but also to give some public assurance about equity. Each of those areas contains about 10,000 cows, and so each area was studied for 5 years with the idea of comparing by log Poisson regression the incidence rates of the disease in the 3 different treatment areas. The stopping rule was to stop as soon as the confidence intervals for the effect of culling were within plus or minus, the 95% confidence intervals were plus or minus 10%. That stopping rule means that you can look at the data as often as politically feasible. It's also the sensible stopping rule, because testing hypotheses doesn't come into it. The notion that all this intense activity was going to have no effect on the disease was not a credible null hypothesis. And I suspect that many other situations where to formulate it as testing problems would be better thought of as estimation. And there's a theoretical literature which justifies, to some extent at least, saying if you stop on that basis, you can, there are no statistical analysis issues. Now, of course, we planned a method of analysis, wrote it down, and we thought we'd, of course, thought of what would happen. But we hadn't, because after about some years, it turned out in our intermediate analyses that the reactive treatment was worse than the control. That it appeared that going in, culling the badgers after there'd been a TB case actually made the future incidence worse. And as soon as that was fairly clear, of course, that particular arm of the trial was stopped. And the final conclusion was that reactive culling increases bovine TB, sustained proactive culling decreases bovine TB. Now, that was a fairly clear-cut statistical interpretation after a very, very careful analysis and also very carefully collected data. But it's a puzzle. It certainly wasn't what we expected. And so it has to be interpreted. And so we say, what is it? Particularly this surprising result. We get a surprising result. We've learned, from one point of view, that's a good thing. One's learned something unexpected. But it has to be explained, and this is what I referred to earlier as interpretation. And there were 2 modes of interpretation. One was provided by animal ecologists of what they call the phenomenon of perturbation. And perturbation is this: badgers have a very set life, they're nocturnal mammals, they have a very set and stable life underground, and they don't travel long distances. But if their social life is disturbed, as it was by the reactive culling, they start to move around much more, reoccupy the depleted areas, and the implicit idea is that when they do that, they deposit, if they're carrying the organism M. bovis, they deposit it more widely, and that was the explanation. The other explanation was that there was a bias in the system that the control group was defective, and what we were actually seeing was that the control group was doing well relative to the reactive group. And how that would come about is this: according to the Berne Convention, culling badgers is illegal except under special circumstances. On the other hand, it's strongly suspected that farmers who tend to believe that badgers are the cause of their disease in cows go out illegally and shoot badgers. It's a sort of form of what in an ordinary clinical trial might be called non-compliance. So the notion would be a farmer in a control area knows that the Ministry of Agriculture is not going to come and shoot his badgers. So he goes out and does it himself to appreciable extent, whereas those in the treated areas will rely on the Ministry of Agriculture to come and do their culling. That was the explanation. How did we resolve this? Well, by a small subsidiary study, which essentially consisted of using the fact that badgers are very fond of peanuts, and painted peanuts were deposited outside the areas in which they live, and the field worker would go around over the next few days and count where droppings from the badgers had occurred. How many would give an indication of the number of badgers, and how far away they moved would give an indication of movement. And that little study, a subsidiary experiment to the main one, showed quite conclusively that the bias control group explanation was not right. I won't go into the details, but that the perturbation explanation was correct. There was another argument that could be used, namely that if this notion that killing badgers haphazardly has a bad effect, it should be that outside the reactive areas, in the proactive areas, heavy culling has gone on. Immediately outside, however, nothing has happened. If this perturbation explanation is correct, there should be a deterioration in the band outside the experimental area, and we had data on a 2-kilometre stretch outside the area, and indeed that had shown an adverse effect. So that was finding something totally unexpected and then resolving it by subsidiary studies. I won't go over that. Now I'm going to turn to some broader issues and ask first of all a rhetorical question. How important is statistical theory? And that really is a rhetorical question. Without theory, each problem is different and has to be tackled by common sense from first principles. Now, there are sometimes certain advantages in that, but on the other hand, it's kind of wasteful of general experience, and also would make very hard going of life for many people. So one needs theory to borrow experience from the past, so to speak, and certainly in teaching the subject, if there isn't a theoretical connecting link, statistics would just become a series of ad hoc tricks. But I think it has to be stressed that the theory of statistics is not a mathematical theory. And it's a conceptual theory. It's about ideas. What are the ideas that we need in order to understand data, see the limitations of data, see the strengths of data, and so on? To translate those concepts into useful ideas, we need mathematics and, of course, computation. But I do think it's essential to, as it were, to get the concepts right first and then do the mathematics that's appropriate, not the other way around, which for mathematicians like myself, it's very tempting to do it the other way around. One likes to do some mathematics, but I think that's a very good thing in almost all respects, but as long as the concepts are correct. Then I turn to a further question, the foundational aspects of statistics. How important are those? Now that is also a rhetorical question, but slightly less rhetorical than the previous question. Because if you think of some other subjects, foundations tend to be quite unimportant. There's a big area, well, unimportant in some sense, there's a big area of the foundations of mathematics. But I think even very, very, very pure mathematicians, by and large, take no notice of this whatever. Again, quantum mechanics is one of the great intellectual triumphs of the 20th century. Fantastic theory, imaginative theory, explain all sorts of exotic phenomena. But the foundations of quantum mechanics, I think, I may be open to correction, are in complete disarray. A few people even say the probability is not needed at all in quantum mechanics. Others say ordinary probability Kolmogorov axioms are okay. Others say we need some special version of probability theory, and there's more than one of those to apply to quantum mechanics. So does that affect the typical physicist and physical chemist? No, I don't think so. They get on and use quantum mechanics usefully. And to some extent, one might think the same is true of statistics. And to some extent it is true, but I think on the whole it's not true, and that the foundational aspects are things we have to think about, at least to some extent. And the contrast here that's typically made is between Frequentist theory and Bayesian theory. Now I'm going to suggest that really that's the wrong way to look at it, partly because there are many versions of both, but also perhaps is not looking at it in the right way. I put here what I call the two phases of Frequentist theory. I'm sure there are more than two really, but here are two. One is that provided by Neumann's more philosophical writings on statistics, we're providing rules of behavior that if we use them again and again and again, then 5% of the time we'd be wrong, let's say. It's saying we can say nothing whatever about any particular case, we're just acting in a way which is such that 5% of the time, or whatever level one chooses, be wrong. And it's led to the parody of saying that a statistician is someone who goes through life trying to make sure that exactly 5% of what he or she does is wrong. And I think that's not quite what we do. Now, there's another way of looking at it, which says that these notions of the properties of our measure, that p-values and, more importantly, confidence distributions are measuring instruments that we apply to our data, subject to, of course, assumptions about the model and so forth, measuring instruments that we apply to our data to help us interpret the data, and that the interpretation, the calibration of these measurements is by saying, if we were to use them again and again in a certain way, then the consequences would be so and so. And it's broadly comparable to the calibration of measuring instruments by, let's say, reference to some international standard or other. When we measure something that's defined by an international standard, we don't actually go to the international standard. It just defines what we're doing. Similarly here, the notion of the proportion of time we're wrong isn't an instruction about how to use the method, it's an instruction about what the values that we calculate actually mean. And the consequence of that is that if this is going to be useful to us, it must apply to the particular data that we're analysing. And R.A. Fisher, who wrote virtually almost entirely from a frequentist point of view, not quite entirely, but almost entirely, he talked about the unique set of data under analysis. You see, in other words, the analysis had to apply to that data. The long-run calibration had to be relevant to that data. And this is connected with notions of conditional inference. The general principle, I think, is absolutely clear. Its implementation is not always clear. There are puzzles about it. This issue, of course, arises more broadly. It's about what might call specificity of information, of aggregate information to individuals. Think, for example, of a clinical trial. A clinical trial has shown the treatment A is clearly better in some sense than treatment B. Now, that says, if one inquires precisely what it means, that had all the people in the trial been treated by A, the aggregate outcome would have been better than had all the people been treated by treatment B, other things remaining the same. But then a treating clinician, and to the extent that I've talked to clinicians about these things, this is the sort of thing they say. They say, well, yes, that's very interesting, but I would like to know for my particular patient that I have in front of me, what is the evidence that A will actually help that patient? When I know about that patient, all sorts of things, obvious demographic things, but also medical history. Why should he think that because in aggregate A is better than B, it should apply to the specific individual? And the answer is, of course, that there's some uncertainty involved. The security, such as it is, comes partly from biological knowledge of how the treatment in question might work, combined with having shown absence of interaction, having shown stability of effect. And the older literature on experimental design, and also to some extent, well, not to some extent, also the more recent industrial, the Taguchi-based industrial experimentation idea, emphasizes this. We put in our experiments factors that are designed to broaden the range of validity of the conclusions and at the same time make them more specific to a particular case. So that's the broad issue involved. The narrow issue involved is that our frequentist theory should be relevant to our particular data, because we want to say that our data, the reasoned interpretation of our data is such and such. So I think there are those two distinctive views. And it's interesting, I think, that Neyman, who wrote eloquently about the first of those, when he did applied work, and he did extensive applied work, when Neyman did applied work, he was doing something very much more like two. He didn't go along with the conditioning idea, but he did do things like say, this is significant past the 10% point and a bit short of the 5% point. He didn't say accept, reject when he was talking about analysis of empirical data, or at least typically he didn't. So there's a clash, whereas to some extent Fisher did. So it's not wise to label these things by particular individuals, I think, is the answer. Now, frequentist theory is contrasted with Bayesian theory. If I have two faces of frequentist theory, how many faces of Bayesian theory? Now, I wrote a paper about 10 years ago called The 5 Faces of Bayesian Theory, and I can't count, that's my trouble. About 3 days ago I had 6 faces, but now I have 7 faces. So here are the 7 faces of Bayesian theory. First of all, I say that by Bayesian theory I really mean the use of inverse probability. That's to say the attachment of probabilities to hypotheses, parameters and so forth, and the application of the standard laws of probability theory. Well, here are the 7 faces, and you may well think of some more. Now, the first of them is the notion that we have a somewhat ill-specified set of similar applications. Supposing we're trying to estimate the mean height of a population of men. Well, there are lots of populations of men we might study. They have different mean heights. Those mean heights have a distribution. We don't really know what that distribution is, but it's likely to be quite dispersed compared with the internal precision of any particular set of data that we have. So it's flat and vague. And I'm really shaky on the history of this, but I think the economist and statistician Edgeworth in the late 19th century and Carl Pearson in the early 20th century, they wrote about Bayesian theory. They didn't always say quite what they meant, but I think the reading is that they had something like that in mind. And it's okay, but it's a fairly limited applicability. Then there's empirical Bayes, which is that you actually see a frequency distribution for the parameters you're interested in. That's totally uncontroversial from all points of view. Then we have the notion, connected but different from one, that a flat plier represents ignorance, that what we want to do is to infer what we can from our data, and so we don't want to put in the prior distribution anything that amounts to tangible information. So we say having a very flat prior does that. Laplace did that in early years of the 19th century. It was strongly criticized in the later years of the 19th century, and really, I think, resuscitated by the great geophysicist Harold Jeffreys in his 1939 book, The Theory of Probability, which is one of the major books in our field. And he, by the notion of the Jeffreys prior, so-called, argued eloquently for that view. And I say from a personal point of view, I first learned about statistics by going to Jeffreys' lectures. So that's an approach, and there have been elaborations of this, particularly by Jim Burgo, Jose Bernardo in Valencia, and earlier also James, which are attempting to justify the notion that it goes under various names, a reference prior and indifference prior, that you can put a prior distribution that means that what you get out is the property of the data. Then there's the notion that the prior distribution that you put in encodes information elicited from experts. They're always, and this raises some interesting questions, particularly about the role of experts. If by an expert, appealing to an expert, you're appealing to authority, you feel that that's in some sense unwise and counter to a general scientific tradition. On the other hand, if you appeal to the knowledge of experts, that's a different matter altogether, and we all do that. And so the idea might be to try and encode the information elicited from experts into a prior distribution and use that, provided, of course, that it was consistent with the data. You're merging the data and the prior. If the two are inconsistent, the inconsistency has to be resolved before Bayes' theorem could be applied. If that isn't done, absurd answers would be obtained. Then there's the very view that was very, very strongly argued some 20 or 30 years ago, that arose from the Cambridge philosopher F.P. Ramsey, but very powerfully from L.J. Savage, from Jimmy Savage, that the probabilities that one uses in this approach are personalistic to you as an individual. You don't have to say where you got them from, but you have to manipulate them self-consistently. So that this was connected with essentially a personalistic approach to individual decision-making designed to put together information in a coherent fashion. My view of this is that it's a very interesting, although certainly not perfect, theory of individual decision-making, but that it's not got much appeal for the analysis of scientific data or its presentation for public policy issues, unless you could show that the issue probabilities involved were strongly evidence-based and held widely. For example, comparing 6 and 5, you might say, in the Badger example that I mentioned, where we have these 3 treatments, should we have elicited priors of the effectiveness of the different treatments? Well, in a sense we did, because there was a kind of public consultation when people could offer their advice. Well, what we found was, knew already really, farmers have a very strong, most of them, not all of them, farmers have a very strong prior belief that the way to get rid of bovine TB is to kill badgers as widely as possible. Veterinary scientists are more neutral. Veterinarians who practice with farmers tend to agree with farmers. Animal ecologists take the opposite view, that the disease is largely caused by poor biosecurity on the farm, in other words, sloppy farming practices. So there were prior encoding information elicited from experts, for which experts, really we were there to avoid doing that because the experts had strongly divergent views. The personalistic use, well, again, very widely different possibilities. I think a subject I think that's not been followed up, but which might be of some interest, is whether the personalistic view would help in clarifying what a scientist in his heart or her heart of hearts really believes about something. Because I think we would all know if we worked with particularly imaginative scientists in a particular field, they may have quite strong views about things that go beyond the data. And maybe the study of that, which would be an exercise in the sociology and psychology of scientists more than in statistical analysis, maybe that would be interesting. And then finally, number 7, the Bayesian method may be claimed to be just a machinery for achieving good frequentist properties. And I put sometimes because if you're not careful with many parameters, it can produce absolutely ghastly frequentist properties that nobody would go along with. So it's not mechanical. Now, the important point of all that is the following. Above all, what are we trying to do? The frequentist is trying to provide methods to show as securely as possible what it's reasonable to learn from your data, given certain assumptions about the data, and of course to have the ability to test those assumptions to some extent. Numbers 3 and 4 and 7 are trying to have exactly the same objective. They're trying to say, what is it reasonable to, what do these data actually tell us? 5 and 6 are doing something more ambitious. They're trying to say, let's merge, let's seamlessly merge information from the data with something else, either personal view in the case of 6 or information elicited from experts in the case of 5. And provided the two sources are consistent, and provided one's satisfied that the prior elicited in 5 has the interpretation of a probability, then, of course, that's a very powerful line of argument. But I think I find difficulties with 3, 4, and 5 with that last point. One can have things that are manipulated as if they were probabilities, but are they really probabilities? If we take something that is relatively, its physical meaning is relatively unclear, you multiply it by a frequency, a model-based probability, and get out an answer. What is it? If you multiply something nebulous by, possibly nebulous, by something clear, is the answer clear or nebulous? Well, it depends. It's the issue of interpretation. Now, I'm not saying that at all that any of those 7 things is, as it were, intellectually wrong. I don't think that's the case. I'm making the point that, first of all, the most important distinction is not between that and the frequentist, but between the view, are you trying to assess the data and leave synthesis with other information to a separate qualitative phase, or are you trying to be more ambitious than that? So that, in other words, puts 3 and 4 in with the frequentist theory, and in contrast with 5 and 6. Well, of course, that's a very inadequate and brief summary of these issues. And I would, perhaps returning to the examples that I gave, all of them were analysed by frequentist methods. I'm sure that numerically very, very similar, perhaps even exactly the same answers could be obtained by Bayesian calculations. The issue is not so much that, but about what the answer actually means. And to me, at least, in those contexts, the frequentist arguments are by far the most appealing. But I'm not dismissing any of those, and certainly 7 can have appeal, and 5 might be very valuable under some circumstances. Well, a summary. We have to recognize the distinctive features of different applications. They're not all, no two are quite the same. We have to try and avoid the fragmentation of our subject. We have to try and emphasize that formal statistical theory is conceptual, get our concepts straight before we rush into a lot of mathematics and a lot of computation. I've said nothing very much about the strategical aspects of statistical analysis, and in particular the need for transparency, or the desirability of transparency. Transparency means that the pathway between the data and the conclusions is reasonably clear. That one should keep things as simple as is reasonably feasible, and here one quotes, one can refer back to all sorts of people ranging from Mozart to Einstein. And then finally, the issue of cautious boldness. The ethos of statistics is cautious, and particularly perhaps in a health context, rightly so. One's constantly saying, well, perhaps this study doesn't quite show what it might seem to. Be careful, and so on. One has to be very cautious about issues of interpretation. On the other hand, scientific research isn't for the timid. It's for the bold and imaginative. And somehow or other, we have to let our caution not inhibit in our both our own thinking and in discussions with subject matter scientists, inhibit this boldness. To some extent, this is covered by my distinction between analysis and interpretation, that by and large, analysis, the fitting of a model, the derivation of estimates of parameters and their standard errors or whatever, posterior distributions or whatever you choose, that should be a cautious process. The interpretation may be bold. Thank you.
There went the computer. I think we have time for a couple of questions if someone would like to ask. And I have to say, I can't see very well. There are microphones in this aisle and that aisle. Oh. Shao.
David, I first want to thank you for giving Bayesian 7 faces. Although I'm quite sure some of the Bayesian would argue they have no faces because they only care about posterior. More seriously, I want to follow up on your comment about these using flat pride to modeling ignorance. I have thought hard about it, and currently I'm thinking that I think that one fundamental problem of Bayesian analysis, the philosophy is really the lack of a coherent way of modeling, ignorance, which probably leads to approach like my colleague R. Dempster's approach, putting ignorance, don't know itself as a special sort of category and trying to go about it. So I just wanted to seek your comments on that type of approach, try and sort of go beyond the Bayesian, so to speak.
Yes, I haven't followed Art Dempster's more recent work. I mean, the notion of, as it were, qualitative probabilities, it didn't, I never quite found that very compelling. And I know he's done with Schaefer quite widely influential work recently, but I must admit I haven't followed it or seen quite what he's achieved that couldn't be achieved some other way. But I have such respect for him that I'm sure there's good things there.
Hi, Xiaolong Lo from Celgene Corporation. Professor Cox, thank you for a very enlightening lecture. I really enjoy it. I have a question. My question is really around whether basic design experiment textbook is outdated, or if you think so, which direction should be updated. The reason I say that is from your first several examples, it looks like the sample is not typically as we commonly use like a two sample or one sample with a two treatment. Your sample is come with an undefined distribution and it evolves according to certain stochastic process. In this country, there is some discussion about adaptive design. I don't know if you have paid attention or heard about it, and that falls into your idea about sampling from a stochastic process. So if we go with that route, it may look like that our traditional experimental design textbook may not fit into that sampling scheme. So my question is whether you have any thoughts that our experimental design textbook is outdated, or if it is, which direction we should revise. Thank you.
Oh, thank you for your question. Well, I wouldn't believe it to be outdated in that the basic principles are just there. In statistical circles, the subject is studied less than it used to be, but that's a sign of the fact that it's been developed to a high degree. I think one has to say, what are the basic principles? Avoiding bias, exploiting the factorial aspect if you can, and asking, above all, asking sensible questions, which is the most difficult point of all. It's true, one doesn't, as a applied statistician, I don't get all that many people coming and asking me questions about design. It's less actively studied in university departments than it used to be. I think that's the message to me is therefore one needs to focus down on the basic principles of design, which I'm sure are very, very important, and focus on the principles rather than on the idea that statistical design of experiments means complicated design. It doesn't mean that at all. The Badger trial that I showed you was very carefully designed according to basically orthodox statistical principles. It didn't mean it was straightforward to do at all, but the principles were orthodox. And as soon as one sees the principles, I think one sees further modes of application. And of course there is the very big area of experimental design and computer simulation, thinking of computer simulation of complicated models as a sort of investigation of a response surface.
Is that someone else?
Yes, I have a question. Dr. Cox, I really enjoyed the talk, and I liked your characterization of the general frequentist approach when you said that basically that the goal of the frequentist approach, if I could paraphrase, was to try to summarize what the data say about your research question. Unfortunately, I think a lot of times frequentist statistics, if I could say so, is viewed as and taught as a way of knowing when to accept or reject hypotheses. And in fact, a lot of people I work with as an applied statistician view that if a p is now less than 0.05, it can't be published, and that they're a total failure. And I think there's a lot of misunderstanding, or a lot of people don't view the frequentist approach in the same way that you described it. I was wondering if you could comment on that.
Yes, well, thank you very much. I think those are important comments that you've made. Well, of course, there is a role for automatic decision-making by, is this significant at some level? Well, not necessarily phrased in terms of significance, but there's a role for automatic decision-making in industrial inspection, for example, and to a limited extent, I suppose, in drug approval by the FDA and the comparable European organization, that for equity, they have to follow fairly set procedures, arbitrary though they might be to some extent. But for scientific interpretation, I think the accept-reject thing is usually inappropriate. And as I said, I think Neyman, who did stress that approach, didn't actually use it when it came to his applied work. But what we should do is teach the subject in a way that is coherent with how it should be used. And one tries to do this, but I don't know how successfully.
So I'd like to close the session by thanking Professor Cox once again and presenting him with a little token on behalf of ASA.
Oh, thank you very much, Lindsay. Oh my goodness. Oh, how beautiful. Yeah, thank you. Lovely, thank you.
So the American Statistical Association recognizes Sir David R. Cox on the occasion of his 2011 President's Invited Address, and with the title,